Welcome to Kotlin Graphics. My name is Romain Guy. I work at Google. I work on a bunch of things, including graphics. I've done graphics programming since the 90s using Java, unfortunately for me, and these days using C++, unfortunately for me as well. So I've been trying to use Kotlin a lot lately for graphics because it's much more pleasant than other languages. And so today I don't want to talk about specific APIs. I don't want to teach you about a specific library or rendering engine. I want to share with you some of the features of Kotlin that maps really well to the field of graphics programming. So some of the things I've learned working on different libraries. So the first one up is Android KTX. So KTX is a library that we pre-announced at the beginning of the year. We announced V1 at Google I/O. It's a bunch of extensions that are specific to Android, and as part of those extensions, there's a set for graphics programming. And obviously, I worked on those extensions. They're mostly meant to be used for 2D graphics programming on Android, but there are some really interesting things in there that you can reuse in various projects. So the first thing that was interesting to do in Android KTX was dealing with legacy code. So on Android, all the colors that we have are defined as integers, 32-bit integers. We call those color ints. We have a special annotation for that to help you in the IDE. But they're extremely verbose to use. They are very error-prone because you have to write this kind of code. So if you want to pack a series of channels, alpha, red, green, and blue, into a color int, you have to do a lot of masking and shifting. And this is where I would normally go on a rant against the bitwise operators in Kotlin, but I'm going to skip that part today. And similarly, when you want to extract the channels for integers, you have to do all that dance as well. So the platform on Android, in our color utility class, we have a few static methods you can use, but they're still a little bit cumbersome to use, and they don't make for code that's particularly nice to read. So one of the things we did was simply use extension functions. So you can declare, or actually extension properties. So in Kotlin, you can add extensions to primitive types. So in that particular case, we added properties to integers. And the nice thing here, you can see we have the alpha, red, and green, and blue properties as read-only properties on integers, and they just do the shifting and masking on your behalf. In addition, you can use the @receiver annotation to specify that those should be used only on integers marked as color int. Normally, the tooling should do the matching for you. I don't think we do for now with Kotlin. But ideally, if you are using those extensions on integers that are not colors, you should be warned. And the result is that when you write your code with those extensions, it looks a lot nicer. The next thing that we did, we went a little step further, and we used these special operators called component1 to component n. So that's for destructuring assignments. Those just map to the properties that we just saw, and they let you unpack a color directly into 4 channels with a destructuring assignment. So we went from all that shifting and masking to using properties to just a single line of code. And I think Andre said it really well this morning in the keynote. It's not about writing less code. It's about writing code that's more readable, and I think that definitely fits the bill. So the first thing I would recommend that you do when you write Kotlin for graphics is try to destructure everything. We have tons of data structure in graphics, rectangles and regions. And there's small classes that only contains a few fields. So just add the destructuring operators to all those classes as much as you can. So here are other examples still taken from KTX. So points, for instance, or rectangle, you can destructure and easily get your X and Y position, or the left, top, and right, and bottom. On Android, you often have to use those. I've also used them for matrices and vectors, so those are not part of Android KTX, but if you do any 3D programming, you're going to end up doing that. So here we decompose a matrix into its 4-column vectors. Also a lot more readable. Or if you have a position like a vector here of 3 floats, you can decompose it in X, Y, and Z. You can see on the slide that we have special operators, the plus and the and. So the next thing that you should do is try to implement operators in your data classes for graphics as well. So there's a series of operators. They're not all listed on the slides, but there's basically 2 categories that we're interested in. There's the arithmetic operators, so the plus, minus, times, and division. And then there's the set operators. So the arithmetic operators make a lot of sense on ints, or if you add 2 points together. But the other ones become very interesting as soon as you do anything that deals with geometry. So a good example is rectangle. If you want to do the union of 2 rectangles, you can override the AND operator. That's normally for bitwise operations, and that's a well-defined mathematical concept. You're going to get the union of both rectangles. The names are a little scary. For instance, the symmetric difference or the complement, those are the official names for those operators. But once you see the APIs, they're super simple. So at the top, for instance, we have an intersection. So the intersection is defined with an OR. So you just take two rectangles, you say OR, and you get the rectangle back. That's just the intersection of both. Symmetric difference, it's the union of both minus the difference. So we use the XOR operator. Then we have path. So if you try to compose path, for instance, on Android, you have to use the up method, and you have to. It's a little cumbersome to use because you have to pass the operator you want to use. It's an enum, so you have to pass like path up dot difference, for instance. Instead, we can just use the minus sign. And you can also mix and match the types. So at the bottom, for instance, you can see that we can offset a rectangle by a point or just a constant float value. So use the operators as much as you can. Another interesting operator that's extremely useful is the contains operator, so it maps to the in keyword. And that one, again, is also very interesting as soon as you do geometry. So anything that's related to heat testing, collisions, or ray tracing, because you're basically shooting rays and you want to know if they intersect with rectangles, this is a very good candidate for this kind of code. So here we add we specify the contains operator on the rectangle class. It takes a point, and the way you use it is this way: if point in, for instance, the bounds of a path. So again, it's not about reducing the amount of code you have. It's about making the code you have a lot easier to read. And it's particularly important because graphics code can become very gnarly. Usually, it's you have like tons of math and memory management. So everything you can do to make it easier to read, please, by all means, do it. And of course, this can be applied to. You could use the in operator with bitmaps and region and paths and anything else that's effectively some kind of boundary in 2D or 3D. One of the operators I didn't mention is the get operator. So the get operator is the square brackets. You've obviously used it on arrays. You've probably used its overload on hash maps with Kotlin. And you can also use it on a lot of graphics types. So in Android KTX, we use it on bitmap. And what's interesting about the get operator is that it can take more than one parameter. So you can pass an x and y, for instance, here to get the value of a single pixel inside the bitmap. You can also override the set operator. Similarly, it can take multiple parameters. The last one is always the value you're setting, and the other ones are basically the location of the value. So here we use this to set the value of a pixel inside the bitmap. The way you end up using it is this way. So we have a bitmap, and if we just say bitmap square bracket of the x and y coordinates, we get our pixel value. And when you combine that with the extension properties that we saw earlier, suddenly you can easily access the alpha channel of a particular pixel of a bitmap. So when you start combining all those features together, again, you make your code way more readable and less error prone. And then inside the branch, you can see that we assign a value back inside the bitmap. We can go a step further. Kotlin has the concept of ranges, so the int ranges, and they're very interesting because they come with a special syntax, the dot dot. And again, the concept of spans or ranges is something that's very common in graphics code. So here, if we override the get operator again on our bitmap, but we specify int ranges, we can effectively define a horizontal span and a vertical span, and they form a rectangle. Which lets you do fun things like this, where we can say, I want to grab a sub-rectangle inside that bitmap, then I want to iterate over all the pixels. And once again, when you combine that with the destructuring assignment that we saw earlier, you have extremely readable code that also happens to be very concise. And you can easily drop the alpha channel if you don't want it. So let's take a look at a more complex example. So if we put all this together, let's say that the user just touched the screen, so we have a point called hit, and we want to see if it's inside the bounds of something. If it is, we're going to create a bitmap. It has a width and a height. Then we want to draw something into that bitmap, and the goal is going to be to look at the value of a pixel inside the bitmap to do a more fine-grained collision detection. So here, we create a bitmap, we scale it, we have to do a difference on our path, because that's what we're trying to render, and we draw. Finally, we get our pixels, and we do the usual dance of extracting the channels. And that's pretty good Kotlin, but there's a lot of boilerplate that's there that makes the logic of what you're doing a little bit difficult to extract from the code. And if you use all the features I just mentioned, the same code becomes this. And there's really nothing magical about it. You're just expressing more clearly what you're intending to do. So next up, I'm going to show you a small demo, because it was a couple of days ago I was supposed to write my slides, but I hate writing slides, so instead I wrote this. Sorry, let me find my, oops. Does it run? It's running somewhere. Sorry. All right. So it's a small ray tracer, actually a ray marcher, written in Kotlin, and of course it's on the wrong screen. Here we go. So it's really slow because it does a lot of computations. It probably allocates a few millions of objects per frame. It computes reflections and shadows. It's a physically based renderer, and you can see reflections in the spheres and on the ground. And this was all written using some of the things I just showed you. So we're going to delve a little deeper into that particular demo to see how it works. It's also heavily multi-threaded to be able to run at a reasonable speed on my laptop. All right, so what I did, actually that demo was ported from a demo I wrote as a shader. So shaders, when you use OpenGL, are written using a language called GLSL. It's the OpenGL shading language. And this is what the code looks like. So it's a little different from what you're used to, but it's not very far off. We have built-in types like vec3 that represents vectors, and then we have a lot of APIs that we can use on vec3s. And using some of the work I've done in a library called Kotlin-math, I was able to effectively copy and paste my GLSL code and port it to Kotlin in about 5 minutes. This is what the same code looks like in Kotlin. So the main difference is that instead of saying vec3 everywhere, you just say val, and you turn your vec3s into float3 constructors, because that's the name of the class I created. And this is really appealing because once you have something like this, you can easily prototype in either language and easily port to the CPU or GPU. Like shaders can be extremely difficult to debug, so you can port your code to the CPU and use the Kotlin JVM debugger, for instance, to step through your logic. And what's really important when doing this kind of exercise is realizing that when you do graphics programming, it's all about the data. You should always model your data first, and everything should fall from that. You should stop thinking about objects too much. Classes, the fewer you have, the better. And math is inherently functional. I've seen a lot of math libraries that just use classes to model like all the math objects, like vectors and matrices. And you end up with very complex APIs, and sometimes it can be very difficult to know when you call, for instance, the dot product as a method on a vector or a matrix. You don't know if it's going to mutate the object or return a new object, and sometimes it does both. So the way you should really think about it is like keep your object as small as possible, use data classes, make them immutable, and write everything else as top-level functions. And that's one of the things I actually love about Kotlin, because, like I said, math and graphics is extremely functional, and the ability to have all those top-level functions maps extremely well to this kind of work. So here's an example of the float3 class I just showed you. So it's basically just a data class, like you do all the time. So declare your data class, add a bunch of operators inside that class. That's completely OK. But then everything else, as much as possible, should be functions. So this is just some of the functions I've used for the demo you just saw. And as you can see, they're just top-level functions. They take one of those float3s, and then they do whatever they have to do. And again, it makes the code extremely easy to read. So this is an example of it's typical 3 programming code. It builds a transform matrix for the camera. So you can specify the eye position, so the position of the camera, the point in the world, the target where you want the camera to look at, and then the up vector. You have to define where up is in that world. And it's, again, like very easy to read, so we use like the minus operator to subtract the vectors. I went a little overboard. I created an infix function called x for the cross product, because it reads better than calling a function cross. But I also have a function called cross. And then normalization, for instance, of a vector is done just as a function. And here are more examples of just using the plus operator, computing the dot product. And all of this, like I said, is compatible with shaders. One of the things that GLSL does extremely well is aliasing and swizzling of members of vectors. So I'm going to show you an example of code so that you understand what those features are exactly. So here we declare a vector of 4 float values, a vec4 in GLSL. And you can grab a subvector by just typing .xyz. But they also have aliased members, so instead of doing .xyz, you can say .rgb, and you get the exact same values out of the vector. It's just, it helps you declare your intent when you're writing your code. Sometimes you want to deal with positions, so you're going to use XYZ. Sometimes you deal with colors, and you're going to use RGB. And they have a few others as well, like ST and UV. And then there's the concept of swizzling. So swizzling is very interesting because it lets you create vectors by selecting the values you want. So for instance, let's say we have a color, an RGB color, but we want to invert the channels. So you can just write .bgr. So we're just accessing the members, but we're accessing them in a different order, and just going to give us a vector in which the values have been swapped. You can also repeat some of the members. If you want a gray version of the color, you can just say .ggg. You're going to get the green channel 3 times in the red, green, and blue channels of your new vector. And those are the kind of things that you do a lot in shader code. It's extremely efficient. It makes the code extremely easy to read and concise. And we can emulate most of it in Kotlin. So here's the way I've done it. For instance, that's from my float4 class, so the equivalent of the vec4. So you can create a bunch of properties with getters and setters. Here, for instance, we have xy that returns just the x and y value of the data class that contains x, y, z, and w. And then for the aliasing, we just create other properties that have different names, like R and G, like RG here. Of course, if we wanted to do proper swizzling, it would be extremely cumbersome because we would have to write all the possible combinations of all 4 members and with all the aliasings that we want. So the class would be just huge. We'd probably want to generate the code for that. So instead, I went with something a little different. So I first created something, an enum called vector components. So those are the names of the different components that you might want to access in the object. Then I overloaded the get operator. It takes one of those enums and just returns the proper member based on the value of the enum. But what's really interesting is when you overload the get operator that takes multiple values, then you can do your swizzling. So we pass multiple vector components, and we'll return a new vector from that. And then the way you can use it is here. So at the bottom, you can see it. We use the square bracket operator. And by doing effectively static imports of the enum, we can have something that's very close to the swizzling that you get in GLSL. It's not quite as nice, but this is about as good as it gets with Kotlin. And again, that worked really well. Like those were the only things really I had to change in the logic when I converted the GLSL code into Kotlin. There were a couple places where I was using swizzling, and I had to modify that by hand. And then obviously the aliasing just works the way it is. Another interesting thing you can do is related to matrices. So there are 2 ways to store matrices, and I think about 50% of the planet likes one way, 50% likes the other way. So you can either store the content of your matrices in row major order, so you store the rows first, and then other people like me prefer to store the columns first. I like to store columns first because when you look at a transform matrix, so this is a 4x4 matrix for 3D transforms, when you look at the columns, they actually have a meaning. Your transform actually describes what's called an orthonormal basis. It's effectively 3 perpendicular axes in 3D space. And each one of the first 3 columns is the direction of those axes. So we have the axis, the right axis, the up axis, and the forward axis. And the last column defines the translation, where you are in the 3D world. So that's why I like to use the column order, because if I say, my matrix square bracket 0, I know I'm getting the first axis, and I find that very convenient. And that's how we use it. So we can use, again, like the get operator with multiple parameters, so you can access a particular element of one of the columns. Now, when you read graphics paper, math papers, research papers, the mathematical notation is row major, and it's not indexed starting at 0, it's indexed starting at 1, which can be extremely error-prone when you're trying to go from one of those research papers into actual code. So the trick I'm using is I overload the invoke operator on matrices, so that's the parentheses. And same thing, because you can have multiple parameters, and because this happens to be the exact notation used in math papers, it feels extremely natural. So if you use the square brackets, you have the column major order, and it's 0-based. But if you use the parentheses, you have the row major order, and it's 1-based. So you don't have to settle for one or the other. You can just do both. Another thing that happens a lot in graphics programming is the fact that whenever you're dealing with one thing, you're probably dealing with more than one thing. And it should be obvious by now because we keep using vectors. Like we rarely use like one float. Use 3 of them or 4 of them. And very often you end up writing code like this. For instance, let's say we want to check that a color is not black. We have to say like if red is greater than 0, and green is greater than 0, and blue is greater than 0. I've been writing this kind of code for 20 years now. and I still have bugs in this kind of, actually when I wrote that ray tracer demo, I used ors instead of ands. So I mess that up all the time. And again, it's kind of hard to read, once you're trained, and if you take the time to read this carefully, it's obvious what it does, but we can do a lot better. So one of the things I've been exploring, and so again, similar to what GLSL does, is using functions and infix operators. So the functions are called, for instance, greater than, and then I have an infix operator called GT. So when you do color, and color is a vector, and so say color GT float 3 of 0, it returns a vector of booleans. It does a component-wise comparison, so it compares every component, as pairs, and it says true or false in the boolean. And then you can use aggregate operators like all, or to say like if all of the values in the boolean are true, then return true. And if you want to use an or instead of an and, you would say any, for instance, instead of all. And so the code we just saw suddenly gets a lot smaller and a lot easier to read, and fewer bugs, which is always a good thing. So next up, just want to mention just one small trick I used in the sample apps for a 3D rendering engine that I work on at Google called Filament. And this slide is mostly here to show you a pretty picture because it's about graphics. So I felt like I had to show you at least one pretty picture. It even moves. And if you're interested, you can look at github.com/google/filament. There's a few sample apps written in Kotlin for Android to do 3D rendering. So anyway, so one of the things I used in those samples turns out that you have to do a lot of data management when you do graphics programming. So you always end up needing small, almost short-lived data types, typically to hold a vertex or a position or part of an object. And the problem with that is you can easily start polluting basically the namespace of your application, your APIs, or you have to make those small classes or small APIs generic enough that they make sense everywhere. But that's it's a lot more work for you. It's a lot more maintenance. So instead, you can use local extension functions. So extension functions, very popular, used all over the place in Kotlin. One of the things that it's easy to forget is that you can declare extension functions inside the function. So here's an example. We want to create a mesh. So in that particular case, there was a cube. So I start by declaring my own data class that's local to that function called vertex. It just takes an XYZ position and then a normal as a vector of 3 floats. And because of the way the API works, the renderer works, I have to create a byte buffer that contains all the vertices. This is pretty common when you use OpenGL, for instance, from Java, and we use the same pattern. So I need a way to write those vertices into a byte buffer. So the best thing to do here is to create an extension function on byte buffer that's local to create mesh. So it exists only here, nobody has to know about it. It's just extremely convenient because I have access to it right there. So all the function does is it calls put float for every float that's part of my vertex. And then when you build your actual byte buffer, so you allocate your byte buffer, and you just call put on it, and you allocate your vertices one by one, and you're building directly the data inside the byte buffer without having to maintain APIs all over your app. Next, I want to talk about some of the features that are in Kotlin 1.3. So 1.3 is not final yet. Andre mentioned them quickly this morning during the keynote, but we're going to look at them into more detail. So the first one is unsigned integers that are called uint in Kotlin 1.3. So they represent natural numbers, and those are extremely useful in graphics programming because we always deal with quantities that are only positive. So anything that's dimensions or pixel coordinates are typically positive only. And it can really help you, uints can really help you make your APIs better. So a great example is, this get operator that we have on bitmap, or this get pixel function we have on Android. It takes an x and y as an integer. But the question is, what happens if I pass a negative value? Will it wrap around? I know that Python libraries love to do that. It's sometimes useful. You pass -1, and actually what it means, the last pixel on the other side. It might throw an exception, it might clamp, or it might, even worse, do nothing and just crash somewhere deep in the stack. So instead, you can use uint to at least guarantee that those values that you're passed are positive. It doesn't help you with the maximum size, you can still pass a value that's outside of the bitmap, but it leaves out some of the potential errors. And what's nice is that you're going to get help from the compiler and from IntelliJ. So if you pass -1, IntelliJ will tell you that the conversion of a signed constant is forbidden when you call an unsigned one. But what's more interesting is how they're implemented. So in Kotlin 1.3 now, those are the types that we have. We have the signed types, byte, short, int, and long, and we have unsigned types. So we have char, which was already there, but char is a little special, and we have uint and ulong. But if you look at the JVM or at Art on Android, we do not have unsigned types that match the uint and ulong. So let's take a look at how they work. We're going to take a very simple example. We create two uints, and then we just add them and store them in another variable. So if you look at the decompiled bytecode, so if you compile for Kotlin JVM and you look at the bytecode, this is what it looks like. So first we load the variable A, then we load variable B, and they're loaded as integers. That's the I prefix on the load operations. And then just does an iadd. So iadd is the operator inside the bytecode just to add two integers. And that's very smart because it turns out that the way signed ints work internally, it doesn't really matter if they're signed or unsigned. Like the addition always works the same way. So that means that uints are effectively free when you add them together. And then there's an invoke static function call. So it invokes a method called constructor-impl. It is not a constructor. If you look at the signature, it takes an int and returns an int. So there's no class there. And we're going to take a look at what happens inside that constructor in a little bit and why it's there. And then we finally store the result of the addition. So if we look at that constructor, it's very simple. It's actually, I would use the word dumb, because it takes an int and then it returns the int that you just passed. So I hope this is just an optimization that's missing from Kotlin C, and I hope that it will go away. I'm sure that in practice at runtime, the JIT or the ahead-of-time compiler on Android will just get rid of this. But right now, there's extra bytecode effectively there for no reason at all. If we look at the subtraction, same thing, just a nice sub instead of an iadd. Multiplication, it's an iml free. It becomes interesting when you do a division. So the division can't be implemented just as a normal integer division, so it has to invoke a static function called uintDivide. If you look at the implementation of that function, it's actually fairly cheap. It does a bunch of ZORs, and it converts everything to longs. So it's going to be a little more expensive, but nothing that you need to worry about. So in summary, I would say that Unsigned Integers are awesome. Feel free to use them. Definitely love them. And so Unsigned Integers, Andre mentioned that earlier this morning, they're implemented with another feature of 1.3 called inline classes. And inline classes are also extremely useful for graphics programming. So they are zero-cost abstraction when you use them correctly. And as graphics programmers, we love zero-cost abstractions because performance matters a lot. So in summary, this is not everything that you need to know about inline classes, but they wrap a single value. You can't have more than one member in an inline class. That value has to be read-only. You can only have one constructor. You can only implement interfaces. You cannot extend another class. You do get equals, hashcode, and toString for free, so it's very similar to data classes. And you cannot use them as var args, which is a little obnoxious because when you look at the implementation of uint and ulong in the standard library of Kotlin, they use them as var args. So Kotlin C has some special magic just for the two types that come from JetBrains, and I'm very jealous. So I want that feature, please, JetBrains. And here's how you declare an inline class. So instead of doing all the hacks that I was presenting earlier where you have an integer that represents a color and you have to put extension properties on them, you can just create an inline class. So the inline class as a single constructor, it takes a private integer, so that's the storage value. And then you declare your method and your property on it just like you would any class. And the beauty of this is that all of this is going to go away. Like the class won't exist. That's what we saw with the unsigned ints. So here's we're going to look at a use case. So we have a var color. We create an instance, for lack of a better word, of that color inline class. Then we call the print function. And the print function just accesses the different properties and then just divides them just to do something interesting with it. So let's look at the bytecode that's generated. So when we invoke the constructor of that color class, inline class, we load the constant, that's that 7f, 10, 20, 30. It invokes the static function that we saw earlier, the constructor-impl. And it's the same thing as with the uints that we saw. It just takes an integer and returns the integer right away. It basically doesn't do anything. And then we store it. And finally, we invoke our print color function. So now if we look inside the print color function, we're going to call it takes only an integer, so the class is gone. There's no instance of our color class. So far, it's free. Then we load that integer. We invoke a static function called getR, so that's to access the red channel. You can see from the signature that it takes an int, returns an int. Again, it's completely free. And here's the complete implementation. That's just the shifting and masking, so nothing interesting so far. So that's great because, like I said, inline classes, zero-cost abstraction, completely free, definitely use them. However, you have to be careful. Just like with the primitive types, int, float, byte, and so on, there are situations where your inline class type will be auto-boxed to an actual instance of the class. And that happens in a lot of situations, but basically if you have nullable types, it's going to happen. If you put your inline class instances inside arrays or collections, it's going to happen. And basically everywhere that you have an API that expects object on the Java side or any on the Kotlin side, you're going to have boxing. And that can lead to very surprising results. So for instance, let's say we have two colors, A and B, and we just want to compare them. Are they equal? And we know that internally they're just an integer, and that should just be an integer comparison. And if we call dot equals on it, it should be the same thing. We should just do an integer comparison. But let's look at the bytecode. So if we look at the bytecode, it becomes very interesting. So we load our integer. That's the iload2 for, I think that's A. Then we invoke a static function called boxImpl, and you can see it takes an integer and returns an instance of color. So here we have auto-boxing. So because we do equals equals, suddenly we've created an object. Then it loads the other variable and does the exact same thing. So if you use equals equals on an inline class that contains only an int, you've created two instances of your color class, and you're creating allocations and putting pressure on the garbage collector. And the reason it does that is because equals equals, it's implemented internally with this r=equal function inside the Kotlin library, and it takes two objects. And because it takes two objects, the compiler has to do the boxing. You can actually improve things. If you do a dot equals b instead of equal equal, that should be the same thing. But there, the compiler is a little smarter. It knows that a is actually an integer, so we load it as an integer, and it stays an integer. Then b is going to be boxed, just like previously, and then it's going to call a function on my class called equals_impl that takes an object. And again, it's because you could be calling dot equals with something that is not a color, that is not an inline class, could be anything else, so it has to accept an object. So the best thing you can do right now to avoid this kind of, if those extra allocations matter, like let's say you're running a ray tracer and it's creating millions of allocations, per second, instead of declaring your storage value in the inline class as private, you can make it public. And then you have to be careful when you do your comparisons. You just compare the underlying values directly. It's a little cumbersome, but it can be helpful. And there are other places where things happen. Let's say you have a string, an empty string, and I want to add my color to that string. So if I do plus equals, it's going to box because it's going to call functions internally that expect objects. But if I do plus equal of a.toString, it's going to call the toString function that has been generated on my behalf that takes an int, and that's going to be free. Coroutines, we're going to talk very briefly about it. There's a bunch of talks this week that you should definitely attend. I'm not a specialist. The real-time running is extremely difficult nowadays because we're trying to render things that are extremely realistic on displays that have a lot of pixels, and we only have 16 milliseconds right now to do this. And it's going to get worse because there are displays coming at 90 hertz and 120 hertz, so you're going to have 8 milliseconds to do all your work. So all modern rendering engines are heavily multi-threaded. And the one I mentioned earlier called Filament, this is a very simplified diagram of the jobs that we create when we render a frame. What happens that basically every single loop inside the engine is multi-threaded. So when you run that on a phone, you have 2 cores, we use 2 cores. You run that on a powerful Linux machine, we use 48 cores, and we go through hundreds or thousands of jobs per frame. And that's exactly what coroutines are for. So in the ray tracer example I showed you earlier, I use the coroutines to render, to use multiple CPUs in the machine to render different tiles on the screen. And it's pretty easy to use. So here, like that's the supervising thread that just runs an infinite loop that renders one frame at a time. It invokes a suspend function called render tiles, and that suspend function is the one that's interesting. It creates a new coroutine scope and then launches a bunch of coroutines in there to render all the different tiles. I had to use, it was interesting because the default scope, the default dispatcher with coroutines has a number of threads that's equal to the number of CPUs minus 1, I believe. And turns out when you do something that's heavily CPU bound, like a ray tracer, that is not enough to keep your CPU busy because the OS will be able to schedule other threads from other apps or background services. So here I'm using my own dispatcher that uses 3 times the number of CPUs in my machine, and I'm basically trying to overload the scheduler. And the difficulty here is to try to find the right number that's not too much and not too little. But by doing that, I went from 50% CPU occupancy to 99.9% of CPU occupancy. Another feature coming to Kotlin 1.3 that seems very promising is scripting. Again, Andre mentioned that very quickly this morning. He showed the KTS files that you can use directly in IntelliJ. But scripting comes with a set of APIs, so you'll be able to create your own scripting environment inside your applications, and I assume it's going to be compatible with multi-platform. I originally wanted to show you an example of using scripting. The problem is that it's very raw. Like they keep changing the APIs, like most of it is not implemented yet. But the point here for graphics is that you end up creating new file formats all the time to define your materials, your scenes, your scripts, your animations. And you spend an insane amount of time writing custom parsers, which is difficult, obnoxious, boring, anything you want. So the idea here would be to use a scripting host inside your application and Kotlin DSLs to basically replace all those file formats. The main issue I see for now is that it relies on the Kotlin C compiler, so you need the Kotlin C jars, at least some of them, embedded in your application, and they're pretty massive, so we're talking like dozens of megabytes that you have to add to your app. So I don't think that's going to be tractable for Android applications, for instance, but anything, desktop server or probably native, that may be good enough. And before we finish, I wanted to talk about some features that I wish Kotlin had. They're not. I tried to be reasonable, and they're mostly inspired by C++. So the first one is the concept of user-defined literals. So here's an example. Now we have inline classes. So let's say I have an inline class called half to represent half floats. So those are floats that use only 16 bits. So the storage is a short, and I have a way to convert to a float, and I have a way to convert floats to half floats. It would be awesome if there was the concept of a suffix operator. So here I could say like float._h, and the _h would be the suffix you put at the end of a constant value. So for instance, when you write 3.1415 for pi, you could say _h, and that would give you a half float. So the workaround right now is to basically use extension functions or extension properties, but I feel a little weird about this because that's not exactly, there's a semantic problem, like I don't want to be actually calling a function, I just want to declare that this is a constant of a very specific type. Floats have the suffix f, longs have the suffix l. And again, unsigned ints and unsigned longs that are implemented as inline classes have a special suffix called u. So why can they have a suffix and I can't? I want it. And could be also useful in a lot of other situations. So here, for instance, for time units, you would be able to write 2.0 underscore like ns, and that would be like 2 nanoseconds, defining whatever time unit you want. The other one that I would love to have is short form constructors. So let's say we have a data class, it's our vec3, takes 3 floats, and I have a function that takes a vec3. And when it's unambiguous, it would be great if I didn't have to repeat myself and say vec3 every time, and for instance, using square brackets. Again, that's something that comes from C++, and it works really well when you're managing a ton of data, especially things like vertices and pixels. And of course, you could nest them, so if you have a vertex that takes 2 vectors, then you will be able to nest the constructors. Linear allocations, I could go for a full hour on that topic. Unfortunately, there's nothing that JetBrains can do about it because it's a problem with the JVM and with Dart. But that would be interesting if they could solve it anyway. And Ryan gave me the idea earlier. We have Kotlin JVM, Kotlin JS, Kotlin native. I want Kotlin GPU. Instead of porting my GLSL shaders to Kotlin, how about I write my shaders in Kotlin directly? All right, if you're interested in some of the code that I showed like in context, that ray tracer, I've put it on Dropbox, the Kotlin-shader toy. Kotlin-math, that's my small math library with vectors and matrices and all that goodness. You can just reuse it on Android or desktop. And then Filament, the rendering engine I was mentioning earlier, the samples are written in Kotlin. And finally, there's 3 very interesting slides if you're talks if you're interested in graphics this week. So mathematical modeling this afternoon at 1 p.m., building a game with libgdx, and then the port of D3.js, a visualization framework, to Kotlin multi-platform tomorrow. So I highly recommend you attend those talks. And I'll be around if you have questions after the talk. Thanks.